Everyone, welcome back to my online channel, The Palm Leaf. This is the 19th video in the data analytics and visualization series. So far, we have looked at a number of different graphs. We've looked at the violin plots, the box plots, the point plots, jitter plots. We've also seen how we could plot text onto a graph. We've looked at the dplyr package, which is in videos 5, 6, and 7, where we could see how we could transform data. So we've come a few places until we get to this video. I hope in the videos before you've been able to look at a different perspective into how you could create really beautiful graphs. Which was not potentially possible, at least to the extent possible in an Excel sheet, right? So I hope this video is also in that direction. In this video, we are going to specifically look at heat maps. So what is a heat map? So in R, if you don't know anything, you just have to put a question mark and just mention what you want to search for. The moment you do a question mark heat map, it will take you to the help page. You can go through the help page. So essentially, what's a heat map? I mean, you'll have a number of different rows and a number of different columns, and each row to each column correlation or each row to each column relationship is handled through a series of colors. So there won't be any numbers that you will see on a heat map. You will just see a range of colors, right? And what you can do with those colors, how do you interpret those colors? It is frankly very simple. I mean, the reason why heat maps are usually looked at is without looking at the numbers. If you want to just understand what is happening, right? So your basic red, amber, green kind of a situation, which will, so anything in red is particularly something that is difficult, or maybe a matrix that has gone wrong, or something that we need to fix immediately, right? And anything that is amber is something that is on the verge of being risky. We need to work on it. And anything in green is absolutely right. I mean, it's working as per schedule. The metrics is green, something like that. So if you have a list of n number of different metrics that you want to track against maybe a timeline, or if you want to compare a couple of metrics, then instead of having every metric evaluated at a number level, right? Instead of looking at the numbers for evaluating a number of different metrics, you can have a quick snapshot, and you can have a single visual view where you can just see all the reds and all the greens and all the ambers, and you can see where those red and greens or ambers lie, so that you can quickly understand, okay, this is the problem and this is not the problem, this is what we need to work on, so on and so forth. So that's the intention of being a heat map. Let's quickly get into the action so that we understand this more better, right? So before we run the heat map, what we need to do is, for any data set, so here we're using the empty cars data set, right? Let's quickly view the empty cars dataset. So we have looked at this dataset before. It is a list of 32 different automobiles, and you'll see all numerical columns, about 11 odd numerical columns, each of them representing some attribute of that car, right? So you have got a Mazda RX-4, you have miles per gallon, number of cylinders, so on and so forth, right? Number of gears, so on and so forth. So before we start using a data set, it has to be converted into a matrix, right? So I mean, just a table or a data frame won't do. If you want to run the heat map usually works on a matrix. So you have to do something called as coercion, right? So you have to just say, and empty cars is assuming that empty cars is just a data set with all numerical columns in them. You will convert everything into a matrix. You just have to write as dot matrix. This is called the coercion in R, and then you assign it to a variable called as dat. I mean, you can give it any name. I'm just giving it dat, right? So I hope you understand this line of code, line number 413. Let me just quickly execute the code. I keep my cursor there, and I press Alt plus Enter on a Windows machine. So that code is executed. Then I move to line 414, and I execute the heat map, right? So what you see here, let me zoom this for you. What you see here is, you'll see all your row names, all the 32 row names on your right. So each row represents each type of car, and each column, as you can see on the x-axis, it represents each attribute of that car. Now the problem is, the reason why you see too much red and only the last two columns seem to be yellow, right? The reason for that is, I'll just quickly show you the empty cars. So what you see in yellow are columns HP and DISP, right? Now, if you look at those two columns, HP, you see that HP and DISP, these are columns with higher number of values in them. The remaining columns are either closer to 0 or 1, or maybe at best closer to 20, right? So it's not able to, so when you look at the heat map, it's not able to distinguish that, right? You have very high values represented by yellow, and the remaining smaller values represented by dark red. So we do something called as normalization. What does that mean? So irrespective of the magnitude of values in a particular column, it will try and normalize it with respect to every column. So for example, if you have, let's say, the cylinder column going from 0 to 10, and if you have the displacement column going from, in the range of 100 to 150. So what it will do is it will try and divide each column by a numerator such that the values move from 0 to 1. And when you draw a heat map on that, each column will be adequately represented, right? And it won't be like a small value versus a big value, but each value will move around within a particular column from its min to max, so that you can look at different columns with different ranges of values normalized in a single view. And I'll just explain that in the subsequent plot. All these tree-like structures that you see on the left and on the top, these are called as dendrograms. So this is something that was used for hierarchical clustering. We'll try and cover clustering separately in subsequent videos. But all that you need to understand is it's just trying to form relationship between different cars, right? And it's trying to form relationship between. So you can see that there's a dendrogram connection between HP and displacement because it's higher number of values, and then it's trying to form that connection with all the rest of the columns because they are smaller values or relatively smaller values, right? Right. Now, let's quickly get into the next lines of code. So that's normalization. So how do you do normalization? Instead of just writing heat map of that, we'll just say scale is equal to column. So it automatically normalizes. And what does that mean? Right now, you don't see deep red all over smaller values. You can independently look at the CYL column and understand that maybe Toyota Corona has got lower values of cylinders, and maybe Maserati Bora has got slightly higher values of cylinders. So anything closer to yellow are higher numbers, anything closer to red are lower numbers, right? So this is a very quick snapshot to understand how your values range. And just to show this to you on the data set, you can see Mazda RX-4 has a cylinder is equal to 6, whereas a Datsun 710 has got cylinder is equal to 4. Now, if you zoom this, if you look at Datsun 710, right, you can see that the first column, the cylinder column, is in red, which means it has got four cylinder. That's the smallest number of cylinders that a car can have in this data set. So that's why you see it in red. But if you look at Mazda RX-4, where is Mazda RX-4? Yeah, it's here somewhere in the bit. You see that it's not red; it's slightly orangish, right? So which means it's getting closer to yellow. That's why you feel, any value that gets closer to yellow is a value that is getting towards the higher end of values in that column. I hope that's fairly okay, right? You can try this around, and you can play around with other data sets which are of numerical value so that you can clearly understand this. Now, now we were looking at empty cars. Now, the thing about empty cars is that it has got row names. Now, let's say you have got a data set which does not have a row name. So what do? Right? Let me run the dplyr package, and you can look at videos 5 to 7 to understand this. So what we're now trying to do is we are looking at the MPG data set, and we are grouping it by manufacturer through the pipe function, and then we're just going to summarize, right? We're going to take the mean of the CTY column, which is city miles per gallon, and the mean of highway miles per gallon. And we are also going to take the mean of displacement and the sum of number of cylinders, right? So you'll get four different columns here, which is mil1, mil2, d1, and c. Right. So mil1 and mil2 are mileage columns. D1 is displacement, and C is the sum of cylinders. I'm going to pass this on to MPG1 dataset. Now let's quickly look at MPG1 because we have grouped by manufacturers. Now it's doing an average of city miles per gallon and highway miles per gallon, and the average of displacement and the sum of all cylinders. It's just an artificial dataset that's been created from the MPG dataset, just so that we can play around with this. Now, as you already know, we have to convert this into a matrix. We are going to look at the MPG1 dataset. We are looking at all rows, but we are only looking at columns 2 to 5. Why is that? Because from columns 2 to 5 are the columns that are numerical in value, right? So we're going to pick that up and pass it on to the DAT. We are going to assign it to the same DAT variable, which is going to be the vector now, right? And now what we're trying to do is in MPG1, we had a manufacturer column, right? Which actually told us what car it is. We are going to pass that argument as raw.name. So we are going to pass on an assignment so that the DAT data frame or DAT matrix gets some row names, right? The moment you get that, you already have a data set with row names. All that you have to do again is just run the heat map, and this is what you get. You get all your columns, mil1, mil2, d1, and c, and you have all your row names on your on the right side, right, along with dendrograms showing the relationship, right? So I hope this was fairly simple. It's an interesting thing you can play around with. Now let's say you just want to remove these dendrograms. They don't really mean anything to you, right? Because it's not easy to consume that data. All that you need to do is you can say heat map with that scale is equal to column. You can use the COL-V is equal to NA and row V is equal to NA. It will remove off the dendrograms both in rows and columns. I'll just show you very quickly. So as you can see here, I have a clean and neat heat map. It tells me it shows me all the different cars that are there, and the artificially created numerical variables of mileage and displacements and number of cylinders. Just to show you how this is, if you look at the C, which is the number of cylinders, Toyota seems to be in yellow and Ford seems to be in yellow. What does that mean? Let's just quickly have a look. So if you go and have a look at Toyota here, where is Toyota? Yeah, you can see the number of cylinders is 174, right? And where is Ford? Ford is 180. So you can see that these two cars have got higher number of sum of all cylinders, and hence they are in yellow, right? The Dodge one is closer to, I mean, it's as good as white because it's the highest number in value. So anything that is closer to yellow or white, you will have the higher number of values. Anything in red will have lower numbers. For example, Honda is 36. You can see Honda in red, right? I hope this was an interesting graph which normally people don't use. I mean, if you want to try this out and see for any of the data sets that you are currently analyzing, it's really cool. Thank you very much for watching. Hope to see you in the next video.